y, the lower function is given by this piece of straight line, all right? And the upper function is given by this piece of the straight line. So I need to find the equation for this and this straight line, all right? In other words, the only thing I need to do is to figure out the equation of the straight line lining together 0, 0, and 4, 8. And that equation is going to be given by y equals half of x. Am I right? Not really, 2x. Okay, 2x. Which means I need a lower function as a straight line passing through 0, 0, and 4, 8. So this equation is given by y is equal to 2x. Okay? I also need to figure out the equation of the straight line lining together 0, 4, and 4, 8. So this is my upper function. Still a line passing through 0, 4, and 4, 8. Okay? 0, 4, and 4, 8. I can easily find out the slope is equal to 1, and it's passing through 0, 4, so it's going to be y is equal to x plus 4. Okay? Y is equal to x plus 4. So I have a lower function, which is 2x. The upper function is equal to x plus 4, and this will be my intergradient region. Okay? This will be my intergradient region, so I write down the double integral with respect to this intergradient region will be x from 0 to 4, y is from 2x to x plus 4, and I'm doing the integration with respect to y first and then x. Okay? So generally speaking, when I give you a double integral, no matter it's x simple or y simple, I'm not going to give you a function you can do evaluation directly. Usually I will give you some information to describe the region. Okay, for instance, it is 1/4 of a disk within the first quarter, or it is a rectangle or triangle with vertices given by 3 points. You need to identify the region, and then you need to extract this information by the location and where the region is. Okay, if it is a y simple region, you need 2 numbers for x, 2 functions for y. So this is my number 2, which is looking like this. A, B, G of x, and G2 of x. So the third type of intergradient region is the so-called x simple region. X simple region will be looking like this. Okay? So my x is bounded by 2 functions now. Y is bounded by 2 numbers. Y is bounded by C and D. Okay? Y is bounded by C and D. X is bounded by the left function with respect to y. So it's going to be h1 of y. And a right function with respect to y as well. So it's going to be h2 of y. And this is our intergradient region. Okay? So if it is x simple region, y is bounded by 2 numbers. X is bounded by 2 functions. But because you need 2 functions to bound x, you need a left function and a right curve. Okay, so comparing these 2 different types of intergradient regions. For x simple region, I need 2 numbers for y and 2 functions for x. Okay, so I need 2 functions of x equals a function of y and x equals a function of y. Okay, and as long as you can write down this, so similarly, I needed to do x integration first, and y integration in the outside. F x y dx dy. Okay. So this will be 2 different formulas for double integral. if I identify the integrating region as y simple, I need to do y inside. If I identify it as x simple, it is x inside. Okay? Again, I can look back to my right angle. I can identify this as an x simple region as well. Okay? I can identify this as x simple region as well. In which way I need two numbers c and d for y, two functions y equals x equals a and x equals b. That with me? Mm-hmm. So this is my left function and this is my right function. So the rectangle is both y simple and x simple. And that is essentially why we can write it in two different forms. Right? That's essentially why we can write it in the x simple region right here and y simple region right here. Okay? So again, we're going to play around with the same game. I give you the simplest example where the function is already written in the x simple form, and we evaluate the double integral. And then I'm going to give you a couple of regions for the identified in order to find whether it is x simple region or not. So let's do this example. So from 1 to 4, from y to 8 minus y, 2 plus 1 over y, dx dy. Again, I want to mention this one more time. Okay, I want to mention this one more time. If you already have the double integral written down in a particular form, okay, in a particular order, you don't have to worry about what the region looks like. You can start your evaluation directly. Okay, you can start your evaluation directly and see whether you can come up with a number in the end. Okay, so the evaluation rule is still the same. I look at the interior integration. Okay, it is with respect to x. I need to find the antiderivative with respect to x for this function. What is the antiderivative function for this guy? 2x plus x divided by 1. Okay. Again, if you're not sure about this is the correct antiderivative, you take the derivative with respect to x and see if you can end up with this function. All right. You take the partial derivative with respect to x, you're getting a 2 plus 1 over y, and this is indeed what you have over here. And I have evaluation x is equal to y to x is equal to y, 8 minus y. Okay? And that is what we have. So plug in here, I'm getting from 1 to 4. So 2, 8 minus y plus 8 minus y divided by y. That's my evaluation at d minus y. At y, I'm getting 2y plus y over y. The whole thing with respect to y. Okay? So I can still verify a little bit. When I eliminate the interior integral, I'm supposed to have a function involving only y. Okay, there should be no x appearing here. Okay, now I can feel safe to proceed. Okay, some of you do this double integral. After they eliminate the interior integral, they still have x in the end. So they're confused, but they still keep going. In the end, you're not getting a number. So you can verify your steps in the middle and see whether you need and whether you can actually go beyond. Here, I can go beyond. I can guarantee you there is a number coming out in the end because there's no x appearing here. Yeah?
So for the first integral, if you do end up having an extra x, do you integrate again with respect to x?
You don't go any further. You go back and see if there's anything wrong.
Okay, so you just never get the chance.
You're never gonna get the correct answer. So after you eliminate in the interior integral, you're supposed to eliminate one variable already. Okay. So there can only be one variable left in this thing. Okay. So here, no x. Okay, there should be no x. After you plug in these boundary values, of course, right? After you plug in this boundary value, of course. So if I simplify the interior, I'm gonna get 16 minus 2y plus 8 divided by y minus 1 minus 2y plus 1 dy. I think you can do the following, right? right?
Would
So
it
this
be
is
minus
a
one
pretty
at the
easy evaluation. Am I doing anything wrong?
The very instead of plus one at the end, it's minus one.
Yeah, -1 here. It should be -1 here. So they're all polynomials or rational functions. So you can easily find all the antiderivatives and plug in values. So in the end, I can indeed get a number. Okay. So I think I did my job before. I think class. So I have 12 plus 8 log of 4. Okay. So that's my number. So evaluating all the double integrals or all the triple integrals, in the end, you're supposed to get a number. You can interpret this number as the signed volume under the surface above a region. Okay? And I want to indeed find easily what this region is. Okay? So I want to find this region in the xy plane. It is written down in the x simple form, which means I need 2 numbers for y and 2 functions for x. All right? I need 2 numbers for y, so y is bounded between 1 and 4. 1 and 4. So this is 1, this is 4. Okay? So this region is definitely bounded between these 2 horizontal lines. I need a left function x equals y and right function x equals 8 minus y. That with me? I need a left function x equals y. So this is going to be my left function. This function is x equals y. And the right function is x equals 8 minus y. So I need to plot this function. So I need a left function x equals y and a right function x equals 8 minus y. Okay? So this is my left function. The right function is going to be x equals 8 minus y. So when x is equal and y is equal to 1, I'm getting a 7. Right? And when x is equal, when y is equal to 4, I'm getting a 4. So it's going to be looking like this. Okay? So this function is x equals y. This function is x equals 8 minus y. And it is bounded between these 2 lines, left and right. So this is my interpreted region. Okay? Always be clear which one is the left function, which one is the right function. The left-hand side function is this function. This curve should be lining on the left of the intervening region. And this curve should be lining on the right side of the intervening region. And it is bounded between 1 and 4. This is the only chance for the region to be. You with me? So within this section, you definitely have to do plenty of practice afterwards. So I want to take a look at this region again. If I take a look at this region again, I already did the y simple interpreted. The y simple double integral is from 0 to 4, from 0 to square root of 16 minus x squared. So I have fxy doing the dy first and dx first. I wanted to stress again, for the rectangle, I can regard it as an x simple region or y simple region. Both of the interpretation will work. For this, it is the same. Okay? For this integrated region, instead of having it as a y simple region, I can also write it as a x simple region as well. So if I want to write it as an x simple region, I need 2 numbers for y. And that 2 numbers is still 0 to 4. I need a curve which is to the left and a curve which is to the right. So the left curve, which will bound this whole intermediate region, will be the y-axis. All right, so this can never go beyond to left to the y-axis, which means I have x equals 0 as my left curve as well. All right, the right curve will be this piece of the arc. Now with me, this is going to be the curve to the right of the intervening region. So you have to be very clear about these geometric relations. Lower, upper, to the left, and to the right. Okay? So this is to the left, this is to the right, and this is going to be a curve which I want to plug in right here. But instead of solving for y, I need to solve for x. I need to solve for x, I need to get a function x is equal to
Square root of 16
minus y squared. So I have square root of 16 minus y squared f xy dx dy. Okay? So here is the final remark I want to make concerning x simple and y simple region. If it is a right angle, you can switch the intervening order directly as long as you keep these intervals correspondingly with x and y. Everything is straightforward, right? If x goes inside, it is AB. If y goes inside, the interior interval should be C to D. If it is x simple or y simple region, I can still switch the order. Are you with me? I can still switch the order of integration, but it will be much more difficult than here. Here, you just need to keep the numbers with x and with y. Here, when I switch the order, not only I need to switch the integrating order, which one goes inside, I also have to figure out all the required information here. Beginning from y simple region, I need 2 numbers for x, 2 functions for y. If I want to switch it to x simple region, I need 2 numbers for y and 2 functions for x. Are you with me? You can still switch the integrating region for x and the y simple regions, but you have to find all the required information one more time. Over the rectangle regions, you don't have to do anything. But for x simple and the y simple region, we have to do a lot. So here is what I want you to practice as many times as possible afterwards. So get your mind straight on this left function, right function, upper function, lower function. So we need to do plenty of practices right here. So I want you to do this one. So I want to write down 0 to 81 from y over 9 to square root of 1, fx1, dx dy. So I want to rewrite it in dy dx. Okay? Dy dx. Which means I want